Section 1.1 Finding Limits Numerically and Graphically. Southwestern College, Professor Maria Olivas. Finding limits numerically and graphically. Objectives. Evaluate limits using graphical and numerical approaches. 1. Limits. Definition of a limit. The function f has a limit L as x approaches a, written, and I'm going to write down the following: limit as x approaches a of f of x is going to be equal to L. If the value of f of x can be made as close to the number L as we please by taking x sufficiently close to, but not equal to, a. If the limit L exists, it must be a unique real number. So I'm going to go ahead and draw a picture to represent this. I'm going to draw a coordinate plane here. I'm going to draw the y-axis, the x-axis. I'm also going to draw a line that goes through quadrant 1 and it has a positive slope. I'm also going to go ahead and erase part of my line, and I'm going to draw an open circle on that line to represent a hole. I'm also going to draw a point directly above that open circle so that we do have a point right above it. I'm going to draw a dashed line going down from my hole to the x-axis. I'm going to draw a tick mark there on the x-axis, and I'm going to label that x value as A. I'm also going to label the x-axis with an X. I'm going to now draw a horizontal dashed line going from my hole to the y-axis. I'm going to draw a little tick mark there, and I'm going to label that y value with a capital L in cursive. I'm also going to label that y-axis with f of x. I'm now going to draw a dashed line from the point that I drew above my hole. It's going to be a horizontal dashed line going to the y-axis. I'm going to draw the little tick mark, and then I'm going to label that y value with an m. It'll be a lowercase m. I'm going to label this entire function here that we see as f. And I'm going to put that in the upper right hand corner of my graph. So to the side over here, to the right hand side, I'm going to write f of a. If I were to evaluate f of a, and I'm highlighting my a value on the x-axis, it looks like here, a lot of people might be drawn to the hole, but we actually have to focus on the point. So we would need to focus on the y value, that is the y coordinate of that ordered pair for that point. So f of a would actually be equal to m. Now if I wanted to find the limit as x approaches a of f of x, I would need to focus here on the left-hand sided limit and the right-hand sided limit to see what value of y we're approaching as we get close to a from the left and from the right. I'm going to highlight in green coming in from the left-hand side as I'm getting close to a on the x-axis, and I'm also going to highlight in green on the function as I'm getting closer and closer to that value of x equal to a, and I'm getting closer and closer to that y value of L here. On the right-hand side, I'm also going to do the same thing. So I'm going to go ahead and highlight on the x-axis, also in green, as I get very close to a on the right-hand side, and I'm going to also highlight on the function in green as I get closer and closer to x equal to a on the right-hand side. I see that I'm getting closer and closer to that y value of L. So the limit as x approaches a of f of x is going to be equal to L. And I've gone ahead and I've highlighted that L value here in green as well. So here, this picture represents what it means to find a limit rather than just evaluating a function at a particular value of x. I'm going to go ahead and draw a cloud around the limit as x approaches a of f of x equals L, because this is what I was trying to represent here visually. Okay, now that we have done this picture, let's go ahead and just talk about the 3 different ways we can actually evaluate a limit. So to evaluate a limit, we have 3 possible approaches. 1, numerically. This means we can select values of x near c and evaluate the function to approximate the limit. 2, graphically. This means we can look at the graph at the function near x equals c and approximate the limit. 3, analytically. This means we can use algebraic techniques to determine the limit. All 3 methods are important and useful, but notice that only method 3 can give us certainty. I'm going to circle the word numerically in our number 1 approach. I'm going to draw an arrow pointing slightly above and towards the right, and I'm going to write down the words. This means you use a table of values. I know sometimes when we see words, possibly like numerically, we might not know exactly what it means, but when you are evaluating a limit numerically, it just basically means we're going to set up a table of values. Graphically, I'm going to circle the word graphically for number 2. This means draw a graph, and we're going to look at the graph, or maybe a graph is already presented to us. And 3, analytically, once again, this means using algebraic techniques, which we will be talking about in our next section. So I will hold off on analytically for now, and we're just going to focus on evaluating limits numerically and graphically for this section. I'm going to go ahead and highlight here that all 3 methods are important and useful, but notice that only method 3 can give us certainty. So if you look at number 1 and number 2, it does say that those ones say approximate the limit, whereas number 3, it will actually determine the limit. Let's move on to some examples. Examples use numerical and or graphical approaches to estimate each limit if it exists. I'm going to underline the words numerical and or graphical approaches, so we're going to be using both of those methods. Example 1. Given f of x equals, and in the numerator we have x squared minus 5x plus 6 all over. In the denominator we're going to have x minus 3. Find the limit as x approaches 3 of f of x. I'm going to begin by drawing a table of values, and I'm going to set this up so it goes horizontally rather than vertically. I'm going to draw a cloud around the word numerically, and next to numerically in parentheses, I'm just going to write down table of values just to make sure it is clear with everybody that when we're doing this numerical approach, we're actually using a table of values to approximate the limit. On the top row, I'm going to label those with my x values. On the bottom row, I'm going to label those with my f of x values. I'm going to go ahead and draw these little line segments here to separate my values, my ordered pairs. For x, from left to right, I'm going to choose the values 2.9, 2.99, 2.999, 3, 3.001, 3.01, and 3.1. When I substitute these x values into f of x, I'm going to get the following values. When I substitute 2.9 for x, I'm going to get f of 2.9 is equal to 0.9, f of 2.99 is equal to 0.99, f of 2.999 is equal to 0.999. If I try to substitute 3, it's going to be undefined, so I'm just going to draw a big X there to represent that that's undefined. F of 3.001 is 1.001, f of 3.01 is 1.01, and f of 3.1 is 1.1. So now that we have our table of values, we can see that as we approach, as x approaches 3, from the left-hand side, and I'm drawing an arrow underneath my table of values, coming in from the left as I'm pointing to 3, and as I'm approaching from the right, and I'm also drawing an arrow underneath my table of values, coming in from the right towards 3, I can see that the values for f of x are getting closer and closer to the value of 1. So I'm going to write down underneath my arrow that was coming in from the left, as x approaches 3 from the left. F of x is getting closer and closer to the value of 1. Now we're going to do the same thing here as we're coming in from the right, or the values that are slightly larger than 3. So underneath the arrow I drew that was coming in from the right, that's pointing to the left, I'm going to write down as x approaches 3 from the right. We're going to now look at the values of f of x, and we're going to notice that those values of f of x are getting closer and closer to the value of 1. So I'm going to go ahead and write down here on the right hand side, I'm going to write the limit as x approaches 3 of f of x equals 1, and I'm going to box in that 1 as our answer. So that's going to be our value that we have approximated for our limit here, as we did this numerically. Let's go ahead and move on to approximating the limit graphically. For the graphical method, I'm going to turn to my graphing calculator. So I'm going to go ahead and input this function in my graphing calculator. I have already input the function. So here I have y sub 1 equals x squared minus 5x plus 6 all over x minus 3. Now that we have input our function, we're going to go ahead and press the graph button to see what the graph of this function looks like. So what we see here on our graph, we see on a coordinate plane where the x-axis is labeled with tick marks from a scale of -10 to 10 by a scale of 1, and the y-axis goes from -10 to 10 by a scale of 1. I see a line with a positive slope, which appears to have a y-intercept at 0, -2, and an x-intercept at 2, 0. I'm going to go ahead and hit the table of values here. So I'm going to go second table, and I can see by looking at the table of values here that I do have an issue here with x equal to 3. So at x equal to 3, there is an error. And that is because if I were to substitute 3, it would be undefined because I would get 0 in the denominator. And I would also get the form 0 over 0 for this particular function if I were to substitute 3 into the function. So I know there's going to be a hole at this value at x equal to 3. So when I sketch my graph, I'm just going to make sure I draw a hole where x is equal to 3. Let's go ahead and switch over to our notes, and I'm going to go ahead and draw in the sketch of this graph. I'm going to begin by drawing in the coordinate plane, the xy coordinate plane. I'm going to draw an x-axis, a y-axis. I'm also going to go ahead and start drawing the tick marks here on the y-axis, going down from 0 to -3 by a scale of 1. And then I'm also going to draw tick marks going upwards on the y-axis from 0 to 3 by a scale of 1. On the x-axis, we're going to go from 0 to 4 by a scale of 1. And then I'm also going to label the x-axis with an x. And I'm going to label the y-axis with f of x. So here we can go ahead and now draw a sketch of the graph of f of x. I'm going to draw the y-intercept here at 0, -2. And I'm going to draw the x-intercept here at 2, 0. There is going to be a hole at 3, 1. And then I'm going to draw another point here at 4, 2. And I'm going to go ahead and I'm going to start connecting here my points, making sure I don't go through the hole that I drew. I'm going to go and extend my line to the ends of the graph and draw arrows on the ends. I'm going to label this function with f of x. In order to demonstrate that I am approaching 3 from the left-hand side, I'm going to highlight on the x-axis in yellow, coming in from the left towards 3. So I'm going to take my yellow highlighter and I'm going to highlight coming in from the left-hand side towards 3 in yellow. And this is going to demonstrate as I'm approaching x equal to 3 from the left. notice what's happening on the function itself. As I'm approaching x equal to 3, from the left, it is approaching the y value of 1, and I'm drawing a dashed line out towards the y-axis where it has 1, and I'm circling it, the 1 value. I'm also going to highlight in green coming in from the right, both on the x-axis as I'm getting to 3 and on the function as I'm getting closer to x equal to 3. And again, I'm approaching 1 for the y's, and so I'm going to highlight that in green, the 1. The limit as x approaches 3 of f of x is going to be equal to 1, and I'm going to go ahead and box in that 1. That's going to be my answer for my approximation here. Note, the limit as x approaches a of f of x exists only if we are approaching the same finite value from both sides of a. These are called one-sided limits and are written as follows. So I'm going to go ahead and write down here the limit as x approaches a from the left. And this, when I say from the left, I'm drawing in, it looks like an exponent of a negative, just the negative right on above the a towards the right hand side of the a. And that's going to represent the limit as x approaches a from the right of f of x. I'm going to write underneath it, x is less than a, because here the values are going to be less than a. And then in quotation marks, the way we read this out loud would be the limit as x approaches a from the left. And then I'm going to end the quotation marks right there. So this, I'm going to now draw some line segments here to separate what I'm going to go ahead and write on the right hand side. And so I have a vertical line segment and a horizontal line segment. I have the limit as x approaches a from the right of f of x. And I'm going to write underneath that x is greater than a, because the values here are going to be greater than a. And in quotation marks, I'm going to write the limit as x approaches a from the right. And in order to represent this, as I wrote this in the limit, where you have a, it's going to look like a superscript of a little plus sign. So it kind of looks like it's in the exponent part, and it's a little plus sign right on the right-hand side, the upper right-hand side next to that a. Example 2, given f of x equals the absolute value of x minus 2 all over x minus 2. Find the limit as x approaches 2 of f of x. We're going to find this both numerically and graphically. Let's begin by finding this numerically. I'm going to create a table of values here. I'm going to set up my table of values horizontally. The top row is going to represent my x values, and the bottom row is going to represent my f of x values. I'm going to go ahead and draw some line segments here to separate my values here for my different ordered pairs. Let's go ahead and switch over to the graphing calculator. I'm going to press the y equals button, and under y sub 1, I'm going to go alpha, y equals, enter to enter a fraction. We're going to need absolute value, so I'm going to press math, right arrow key, enter on number 1 for absolute value. Then we're going to input x minus 2. Down arrow key, and we're going to input x minus 2. Now we're going to go second and quit. I'm going to show you another way to evaluate this function. We're going to go to VARS for vars or variables, right arrow key, enter, and then enter again. Y sub 1, open up a set of parentheses, and we're going to input 1.9, close the parentheses, and then press enter. And we get -1. Let's do this process again. So we're going to hit the VARS button, right arrow key, enter, enter on 1 for y sub 1, open up a set of parentheses, and we're going to input 1.99, close the parentheses, and enter, and we get -1. And then once again, vars, y sub 1, open up a set of parentheses, 1.999, close the parentheses, enter, and we get -1. These represent values coming from the left. Now let's do values coming in from the right. Vars, y vars, enter y sub 1. Open up a set of parentheses, and we get 2.001. Close the parentheses, enter, and we're going to get positive 1. Vars, y vars, enter y sub 1. Open up a set of parentheses, 2.01. Close the parentheses, enter 1. Vars, y vars, enter y sub 1. Open up a set of parentheses. We get 2.1 here for our x value. Close the parentheses, enter, and we get 1 for y. So it looks like we're getting values of -1 to the left of 2 and +1 to the right of 2. If I go to the graph button, I'm going to notice here on my graph that to the right hand side of 2, it looks like y equal to 1, a horizontal line, and to the left hand side of x equal to 2, I've got a horizontal line there at y equal to -1. If I were to look at the table of values, second table, I'm going to notice here that at x equal to 2 it says error, but all the numbers that are less than x equal to 2 are going to be y values of -1, and all the numbers that are greater than x equal to 2 are going to be y values of 1. So this tells me that the right-hand-sided limit is not equal to the left-hand-sided limit. Let's go ahead and write down these values. For the x values from left to right, it's going to be 1.9, 1.99, 1.999, 2, 2.001, 2.01, and then 2.1. For our f of x values, f of 1.9 is going to be equal to -1, f of 1.99 is -1, and f of 1.999 is -1. If we enter x equal to 2, it's undefined, so I'm just going to draw a big X there, and I'm just going to write the word error underneath, but you guys can also write undefined if you want. And then f of 2.001, f of 2.01, and f of 2.1 will all be equal to 1 each of those. I'm going to go ahead and lasso in my entire table, and I'm just going to shrink it a little bit, and I'm going to raise it up slightly more so I have a little bit more space to write underneath it. I'm going to go ahead and draw like a big curly bracket underneath my values here for x equal to 1.9, 1.99, and 1.999, and underneath it I'm going to write the limit as x approaches 2 from the left of f of x is equal to -1. And I'm also going to draw a big curly bracket underneath the values where x is equal to 2.001, 2.01, and 2.1, and I'm going to write the limit as x approaches 2 from the right of f of x equals 1. So here you can clearly see that the limits are not equal to each other, the right-handed limit and the left-handed limit. I'm going to circle in each one of those limits and draw arrows to each one, and I'm going to write down the words not equal so that we know that these two limits are not equal to each other. For the graphical method, I'm going to draw a coordinate plane, an x-axis and a y-axis. And I'm going to go ahead and recopy the graph that we saw on our graphing calculator. So at x equal to 2, I'm going to draw tick marks here on the x-axis going from 0 to 2, and I'm going to label those. And I remember that you can't have x equal to 2, so I'm going to have to draw a hole. So I'm going to draw a hole at 2 points here. I'm going to draw one hole at the ordered pair, or the where the ordered pair should be, of 2, 1. And I'm also going to draw a hole at 2, -1. I'm going to write down that ordered pair right next to that hole. To the right-hand side of x equal to 2, I'm going to draw a horizontal line that looks just like y equal to 1. And then I'm also going to label in some more values here on the x-axis from 0 to -2 by a scale of 1. And I've also labeled in on the y-axis from -1 to 1 by a scale of 1. I'm going to draw a hole at 2, -1. And then to the left-hand side of x equal to 2, I'm going to draw a horizontal line that looks just like y equal to -1. And I'm going to label the ordered pair right underneath that hole so you know where that's at. That's going to be at 2, -1. So that's what our graph is going to look like. So once again, if we were to approximate this limit graphically, I would look to see what is happening here as I am approaching 2 from the left-hand side. I can tell by looking here at the function. The limit as x approaches 2 from the left of f of x is going to be equal to -1. And I drew a big curly bracket right underneath the part where I can see that part of the line, like to the left of x equal to 2, that looks like a horizontal line at y equal to -1. And I drew a big curly bracket above the right-hand side where x of x equal to 2, where it looks like a horizontal line, y equals to -1. And I wrote the limit as x approaches 2 from the right of f of x equals 1. So once again, the right-handed limit and the left-handed limit, they are not equal to each other. Therefore, the limit as x approaches 2 of f of x is going to be equal to, I'm going to write the letters D, N, E, and those letters represent does not exist. So that limit does not exist. And I'm going to box that in as our answer. Let's move on to example number 3. Example number 3 says the following. Given f of x equals 3 when x is greater than 0 and -2x when x is less than or equal to 0, find the limit as x approaches 2 of f of x, the limit as x approaches -1 of f of x, and the limit as x approaches 0 of f of x. So here we have a piecewise defined function. We're going to have to graph this to really understand what the limit is for each one of these. So I'm going to go ahead and draw a coordinate plane here on the right-hand side. My coordinate plane is going to focus more on quadrant 1 and 2 so that I have a better picture of what I'm trying to find here. And now what I'm going to draw f of x equals 3 when x is greater than 0. So that's going to be a horizontal line that looks just like y equal to 3 when x is strictly greater than 0. I'm going to have to draw an open circle right at 0, 3 because it can't equal 0 since it says x is strictly greater than 0. So here I am highlighting the x-axis to the right of x equal to 0. I'm drawing tick marks here that go from 0 to 3, scaled by 1, and then an open circle at 0, 3, and then a horizontal line that looks just like y equal to 3 to the right. So now I'm going to draw f of x equals -2x when x is less than or equal to 0. First, I'm going to label my open circle here that I just finished drawing at 0, 3. Now I'm going to go and draw f of x equals -2x, and I'm going to highlight f of x equals that -2x part and the inequality that represents our domain for that piece, which is x is less than or equal to 0. I'm going to write that up here above my coordinate plane. F of x equals -2x plus 0. So here x is less than or equal to 0. So I'm going to go ahead to my y-intercept for that piece of the function, which is going to be at 0, 0. And I've highlighted the origin, and then I've highlighted to the left of the origin in green, right on top of the x-axis. So I know this is the domain, the part of the domain that I'm working with right now. I'm going to draw a point right on top of the origin, right at 0, 0. I'm going to go ahead and draw some tick marks here on the x-axis. I'm going to label those from 0 to -2 by a scale of 1. I need the slope in order to come up with another point. So the slope here is -2. But I'm going to write this as a fraction with +2 over -1, so that way I know that I can go up 2 and over 1 to the left. So I'm going to go up 2 units and then over 1 to the left. It's going to land me right at the ordered pair -1, 2, and I'm going to label that ordered pair for that point, connect my 2 points that I have, and extend my line to the left-hand side and draw an arrow on the end of that line. I'm going to erase the work I did here for that function and the slope that I came up with. Now looking at this graph, I can come up with the answers to A, B, and C that I have here on the right. So for A, we have the limit as x approaches 2 of f of x. So now I'm going to focus where x is equal to 2 on the graph. I don't have my tick marks labeled there on the right hand side for the x-axis, so that's what I'm going to do. I'm going to label my tick marks here from 0 to 3 by a scale of 1. Now I'm going to focus as I'm approaching 2 from the left and from the right. And I'm drawing these arrows underneath where x is equal to 2. I'm also going to highlight on the actual function as I'm approaching x equal to 2 from the left and from the right. And I'm drawing a dashed vertical line coming down to x equal to 2. So that way I'm kind of focusing in on this value at x equal to 2. The ordered pair here is going to be, and I'm drawing a point right of that point, right on the function, and I'm labeling the ordered pair with 2, 3. Because the y value is 3 here, I'm going to be approaching 3. So I'm going to say the limit as x approaches 2 of f of x equals 3, and I'm going to box that in as my answer. Now, I'm going to extend some more tick marks here on the y-axis. So I'm going to go up to 1, 2, 3, 4, 5, 6. So I'm going from 0 to 6 by scale of 1 on the y-axis. Here on B, it says the limit as x approaches -3 of f of x. So now I need to focus on that x value of -3. So I'm trying to see what am I approaching as I get closer and closer to x equal to -3 from the left-hand side and from the right-hand side. I'm going to draw that ordered pair or that point that's on the function at x equal to -3. I need to know the y value of that ordered pair. So I'm just going to label a few more points here for my function. I'm going to label the point -2, 4, and then I'm going to label that point -3, 6. So as I'm approaching -3 from, well, first let me draw a dashed line going from -3 on the x-axis up to that ordered pair so you can see that it lines up. And now as I'm approaching -3 from the left and from the right, I'm going to be approaching the same y value of 6. So the limit as x approaches -3 of f of x is going to be equal to 6. And I drew that dashed line that connects to 6 on the y-axis so you can see that that's the y value it's approaching. And I went ahead and wrote that in here, and I boxed in the 6 for my answer. C, the limit as x approaches 0 of f of x. So now we're going to focus where x is equal to 0, and we're going to see what is it value of y is our function approaching here as the closer and closer we get to on the left-hand side as x approaches 0, and then also from the right-hand side, what y value are we approaching as x approaches 0 from the right. So let's go ahead and look at our graph this time and see what we can see here. So I know I have a lot of things drawn here on my graph, but I'm going to draw arrows at the very bottom to show you, to represent the part that represents limit as x approaches 0 from the left of f of x. And then I'm going to draw an arrow coming in from the right to represent the limit as x approaches 0 from the right of f of x. So if we look and we focus on the parts that represented the function, I can see that as I'm coming in from the left, the y value that it's going to be approaching is 0. And as I'm coming in from the right, it's going to get closer and closer to the y value of 3. So the left-hand sided limit and the right-hand sided limit, I'm circling those limits, and I'm trying to show you that these two limits are not equal to each other. So when the left-hand sided limit and the right-hand limit do not equal each other, we say the limit does not exist. I'm going to rewrite this right over here on the side right below the C part. I'm going to write the limit as x approaches 0 from the left of f of x equals 0. The limit as x approaches 0 from the right of f of x equals 3, so that you can clearly see here that they are not equal to each other. I'm going to point arrows at the 0 and at the 3, and then I'm going to write the words not equal right next to it. And then for C, where it says limit as x approaches 0 of f of x, I'm going to say it equals DNE, which stands for does not exist. And I'm going to box that in. So that's going to be our example number 3. All right, let's go on to our next example. Example number 4, given f of x equals x when x is not equal to 1, and 3 when x equals 1, find the limit as x approaches 1 of f of x and f of 1. So in order to do this problem, I think it's important to draw a sketch of the graph. I'm going to draw a coordinate plane here towards the right-hand side of the screen. And now I'm going to draw a sketch of what this graph looks like. It's going to look like y equals x almost everywhere, except at x equal to 1. So I'm going to go ahead and on the x-axis, I'm going to draw tick marks from 0 to 4 by a scale of 1. And then on the left-hand side of the x-axis, I'm going to draw tick marks from 0 to -4 by a scale of 1. On the y-axis, I'm going to go from 0 to 4 by a scale of 1. And then towards the bottom, I'm also going to draw tick marks on the y-axis from 0 to -4 by a scale of 1. Now that I have drawn my coordinate plane and labeled my two axes, I am going to go ahead and focus on the first piece of this piecewise defined function, which is the f of x equals x when x is not equal to 1. I'm going to highlight that piece in yellow. I'm also going to rewrite that equation right over here on the right-hand side, right above my graph of my coordinate plane here. I'm going to write f of x equals x, comma, when x is not equal to 1. Now I need to know exactly what we have going on at x equal to 1. So I'm going to go ahead and substitute f of 1, which equals 1. And I'm going to get 1 comma 1, and I know this is going to represent a hole. So I'm going to write the word hole with an arrow pointing at it. I'm going to draw a hole on my coordinate plane, and I'm going to label that hole with 1 comma 1. And I'm also going to go ahead and start drawing the points here for my graph of y equal to x, or f of x equals x. And I'm going to be careful to make sure that I draw my line everywhere except in that 1 comma 1 area, which is a hole. So I have extended the function all the way to the end. It looks just like a line, looks just like the line y equals to x, and I've drawn arrows on the end, except that 1 comma 1, which is a hole. I've gone ahead and I've highlighted in green f of x equals 3 when x is equal to 1. This is just going to represent 1 point. And I've drawn some curly bracket, one curly bracket right underneath the 3 when x is equal to 1. And I've written point at 1 comma 3. So I've gone to my graph, I've drawn a point at 1 comma 3, and I've labeled it with the ordered pair 1 comma 3. Here is the graph of my function. So now I can find the limit as x approaches 1 of f of x, which I have circled that piece right there, that part in the problem. I'm rewriting it over here to the left-hand side. The limit as x approaches 1 of f of x equals, and I'm going to focus on my function, and I'm going to see what is occurring the closer and closer I get to x equal to 1, both from the left and from the right. It looks like I'm getting closer and closer to the y value of 1, and I've gone ahead and I've circled that y value of 1 on the y-axis and the y value of 1 on the ordered pair that I wrote next to the hole. So I've gone ahead and written the limit as x approaches 1 of f of x equals 1, and I've boxed in that 1. Now I need to evaluate the function at x equal to 1. So f of 1 is going to be equal to, looking back at my function, when x is equal to 1, I've drawn a dashed line headed up to that ordered pair 1 comma 3, and I've circled the y coordinate on that ordered pair of 3. So f of 1 equals 3, and I have boxed in that 3. So for example 5, it says, given the graph of f of x shown, find each limit. And here for f of x, we have a coordinate plane that's focused in quadrant 1 and quadrant 2. We have a closed circle point at -1 comma 2. At x equal to 1, on the left-hand side and the right-hand side, we have two different pieces of a function. So on the where x is equal to 1, there is a closed circle at 1, 2, and then to the left-hand side connected to it is a piece of a line with a hole at -1, 4. And then at x equal to 1, we have a hole or a open circle at 1, 1, and then to the right of that we have a piece of a line with a positive slope, right, going to the right. A, the limit as x approaches 1 from the right hand side of f of x. I'm going to highlight the x approaches 1 from the right hand side. I'm going to highlight the 1 on the x-axis, and I'm going to highlight coming in from the right, from the x-axis and on the function. I notice it's approaching the value of y equal to 1, so I'm going to circle the 1 and I'm going to draw a dashed line kind of connecting it to that value there at x equal to 1 where the hole is at. So limit as x approaches 1 from the right of f of x is equal to 1. Now B says the limit as x approaches 1 from the left of f of x, and I've highlighted x approaches 1 from the left underneath the limit in green, and I'm also highlighting in green on the x-axis and on the function what is happening as we're approaching x equal to 1 from the left. I notice that we're getting closer and closer to the value of y equal to 2, so I'm going to write the limit as x approaches 1 from the left of f of x equals 2, and I'm going to box that in. For C, the limit as x approaches 1 of f of x. I'm looking at part A and part B. I'm noticing that these two limits, the right hand limit and the left hand limit, are not equal to each other. So I've pointed arrows at both of these values for these limits, and I'm writing to the right, these values are not equal. If the right hand limit does not equal the left hand limit, then that means the limit does not exist. So I'm going to write here the limit as x approaches 1 of f of x equals dne. For does not exist, and I'm going to box that in. All right, part D, the limit as x approaches -1 from the right of f of x. I'm going to erase everything that I had written here on my coordinate plane so that I can start highlighting things again. I'm going to highlight the x approaches the -1 from the right, and I'm also going to highlight as x is approaching -1 from the right here on the x-axis and on the function. We're getting closer and closer to the value of 4 on the y. So on the y-axis, I've circled the 4. And for D, I've written limit as x approaches -1 from the right of f of x equals 4, and I've boxed that in. E, the limit as x approaches -1 from the left of f of x. I've highlighted the x approaches -1 from the left in green. I've highlighted coming in from the left on the x-axis and the function in green. And I see we're approaching 4 as well, so I'm going to go ahead and write that equals 4 and box that in. I'm circling part D and E, and I'm also going to draw arrows to those two values, and I'm going to write to the right of these that these values are equal. Since these values are equal, and the right hand limit is equal to the left hand limit, therefore, the limit does exist. So for part F, the limit as x approaches -1 of f of x is going to be equal to 4, the exact same value of the right hand limit and the left hand limit. So I'm going to go ahead and write that in, and I'm going to box that in.